Here comes the fabulous announcement again. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I respond as soon as I can. I feel like one of those infomercials where they're trying to shove 5 minutes worth of information into 30 seconds. Okay. All right, so continuing on, still in section 8.2 that talks about functions. Let's see here. Let's go all the way down here. We looked at a couple of examples earlier where we put a function input in and we got undefined, and I said that that input was not in the domain because it didn't produce a real output. When I was a kid, my mom had a meat grinder, and it was made of pot metal. I don't know if you know what pot metal is, but it's pretty cheap, pretty thin. In fact, if you ever try and weld something with pot metal, it pretty much just blows it away. You can't do it. Well, we had this meat grinder, and you put like roast beef in it and turned the crank, and out came these little, looked like spaghetti noodles. They kind of looked like worms, really, but tasted great. I mean, they weren't worms, but it just came out in a strain. So the idea is you put meat in, you turn the crank, and you get this ground up meat. Well, my brother, he put a rock in the meat grinder. What do you think happened? Anybody? No volunteers. I'm so lonesome all by myself. Okay, fine. Well, it broke the meat grinder. Why would you put a rock in a meat grinder? It's not a rock grinder. So a rock was not an appropriate thing to put into a meat grinder. And by the way, that's not true. It is true about the meat grinder, but my brother didn't put a rock in it. So if you see him, don't tell him. All right. Anyway, so my point is this. When you put something in and you don't get something out that's acceptable, then what you put in should not have been put in, okay? So if you put a number into a function and the output is undefined or something that's not real, then that input is not in the domain of the function, meaning you should avoid it. Now, let's say I have the following function, h of x equals 3x plus 6. It says, find the domain of each function. So my question to you is this: is there any value of x, any domain, potential domain value, any number that if I put it in there, I would get something that was undefined? Now remember, undefined means we're dividing by 0. Well, if I take 3 times any real number, I'm going to get a real number, plus 6, I'm still going to get a real number. Okay, so if I put any real number in there, okay, so the domain of this function is all real numbers. Now, I'm going to look at something called interval notation. A lot of what we're going to be doing today refers back to the Math 85 or the Math 84 class. In chapter 2 of this same textbook, we would have talked about interval notation. The way you'd say all real numbers with interval notation is you'd have parentheses and then you'd have negative infinity, comma, infinity. That means that the answer goes from negative infinity to positive infinity inclusive, except that I've got parentheses around the negative infinity and parentheses around the positive infinity. It doesn't include endpoints because there is no specific point called negative infinity. There is no specific point called infinity. So this just implies keep going in both directions forever, okay? So the domain of this function is all real numbers written in interval notation. It would look like that, okay? Now, let's take a look at another example. F of x equals 1 over x minus 4. And again, we want the domain. Okay, now we have a variable in the denominator. Is there a value or values of x that if I put in the denominator, we would be dividing by 0? Now, it's not x equals 0, because if x was 0, that would be 1 over negative 4, and that's not 0. But what if I put 4 in there? What would f of 4 equal? 1 over 4 minus 4, 1 over 0, which is undefined. Okay? So the domain is x is not equal to 4. Or you could say the domain is all real numbers except 4. But we're going to say it in interval notation. Now, in the previous example, it was all real numbers. I want all real numbers excluding 4. So this is how I'm going to write that. It's going to go from negative infinity up to 4. But I'm going to use parentheses on the 4, meaning that we go up to 3.9999999, but not 4. And then we're going to have the union of that and everything after 4. Now, granted, this is much simpler and more efficient than this, but as you move along in mathematics, they will be using this idea of interval notation quite a bit, so we need to get used to it. Okay, so this is interval notation. This little u means union. It means all of this along with all of that. Okay, and again, this is back from chapter 2. I think it's like 2.6 or 2.7 if you want to refer back to it. Okay, now how about this? G of x equals the absolute value of x minus 7. Do you remember what an absolute value is? If you take the absolute value of a positive number, you get a positive number. If you take the absolute value of a negative number, you get a positive number. If you take the absolute value of 0, you get 0. Absolute value is the distance from a number to 0 on the number line, and distance is always positive or 0. Okay. Now, is there any value of x that if I put it in there, so I take a real number minus 7, and I take its absolute value, would we ever get something where we're dividing by 0? No, you might get 0 or some positive number, but you wouldn't get dividing by 0. So here the domain, again, is all real numbers. All right. What about, let's see, this one? S of x equals 9 divided by 2x plus 1, the domain. Well, this one's a little trickier. It's not quite as obvious to see, but let's go back here to this one, okay? Another way of solving this, we just kind of looked at it and I said, oh, 4 minus 4 is 0. But what you don't want the denominator to equal 0. Well, when would that be 0? When x is 4. So here, we don't want the denominator to equal 0. We don't want 2x plus 1 to equal 0. So what if we solve this and find out when this would equal 0? So subtract 1, 2x equals negative 1, divide by 2. So that's the bad guy. That's the number that's going to make this thing undefined. S of negative 1/2 is going to be 9 over 2 times negative 1/2 plus 1, which is 9 over negative 1 plus 1, 9 over 0, undefined. Okay, so the domain x is not equal to negative 1/2. How do we write that in interval notation? Negative infinity up to but not including negative 1/2 in union with after negative a half up to infinity. Okay. Let's see here. Let's take a look at one more of those. How about this? What is that? T of x equals 15 over 1 minus 3x. So again, my suggestion is, since there's a denominator with a variable, find out when is that going to equal 0. Okay, well, let's see. If I add 3x to both sides, 1 equals 3x, divide by 3, x equals 1/3. And I don't want that to happen. So my domain, so basically we're finding the bad guy, goes from negative infinity up to 1/3, but it doesn't include it, and then 1/3 to infinity. Let me remind you of something from a past course. If I wrote it like this and I used a bracket, that would include 1/3, but a parenthesis means you go up to it, but you don't include that actual number. Okay, all right. Next, it says graph each function. So we're going to go way back here. And we're going to take a look at this first one. It says f of x equals 2x minus 1. All right. Now, there are a couple of different ways we can graph this. And what we're going to be looking at here, I think, for the rest of today is something that's a review of going back to chapter 3. And I know some of you took beginning algebra a long time ago, so this is all going to seem like new stuff, but we're going to go through it here. So f of x equals 2x minus 1. One of the ways we can graph this is to recognize that this function is in what is called slope intercept form. That is y equals mx plus b, where m is the slope and b is the y-intercept. Okay, so in this case, the slope would be 2, or 2 over 1, and the y-intercept would be -1. Now, how does that transfer to the graph? Well, the y-intercept is the point where the graph cuts through the y-axis. So that would be right here. That's the point 0, -1. The y-intercept is at -1. The slope tells what the graph does going from left to right. It goes up 2 and over 1. So up 2 and over 1, up 2 and over 1, up 2 and over 1. That is the slope of the graph. So having established a point, the y-intercept on the graph, and then using the slope to establish more points, there is the graph of f of x equals 2x minus 1. Okay? Now, there's another way to graph this same function. So let's take a look at that. We can make a table and find some ordered pairs. How about if we let x equal 0, 1, and 2? Okay. If x is 0, f of 0 is 2 times 0 minus 1, which is 0 minus 1, which is -1. So 0, -1 is a point on the graph. If x is 1, f of 1 equals 2 times 1 minus 1, which is 2 minus 1, which is 1. So 1, 1 is a point on the graph. If x is 2, f of 2 equals 2 times 2 minus 1, 4 minus 1, which is 3. So 2, 3 is a point on the graph. Now, 2 points is enough to establish a line, but I found a third point just to make sure that I didn't mess up, because if all 3 points line up, there's a good chance I've done it correctly. If they don't all line up, I know something's wrong. And notice that that's the same graph as that one, okay? So a couple of different ways we can graph these functions. Any questions on that before I go on to another example? I know I'm giving you a lot of stuff today. All right, how about this one? F of x equals 2/3 x minus 2. So if we use slope-intercept form, the slope is 2/3 and the y-intercept is -2. So we'd start y-intercept at -2, we'd go up 2/3, up 2/3. And we'd get the graph. Okay. Now, what if I want to do it finding ordered pairs instead? So I'll make a table, and I'm going to use 0, and then I'm going to use 3 and 6. Now, why did I use 3 and 6? Because those are x values that are multiples of this denominator, so they're going to reduce out and give me nice numbers. Okay, if x is 0, we've got, let's see, we'll go over here. F of 0 equals 2/3 times 0 minus 2, which is -2. Can you see that over there? Or is that being blocked by the pictures of us? It's okay. All right. Let's see. F of 3 is 2/3 times 3 minus 2. The 3 is reduced. 2 minus 2 is 0. So 3, 0. Oh, there's that. If x is 6, f of 6 equals 2/3 times 6 minus 2. 6/3 is 2/1. 4 minus 2 is 2. 6, 2. So we get the same thing. All right. So again, slope-intercept form or finding ordered pairs, you can graph the linear function because it's a graph of a straight line. Okay. Now what I'm going to do is I'm going to close this without saving it and open it up again so that I have some more grids. Okay. How about this one? F of x equals -x. Well, slope-intercept form, this is like y equals -1x plus 0. So your slope is -1/1 and your y-intercept is 0. So that goes through the origin and goes down 1 and over 1, down 1 and over 1, down 1 and over 1. So there is using y equals mx plus b, slope-intercept form. Okay. Or making a table. Let's see, how about if we use 0, 1, and 2? F of 0 is -0, which is 0. So that's that point here. Let's do that in red. It's that point. F of 1 equals -1. So that's 1, -1. That's that point. 2, f of 2 equals -2. So 2, -2, that's that point. So again, you get the same graph. All right. One more example. What about this? F of x equals 2. Well, if I wrote that in regular notation, that would be y equals 2. So this is something coming from, again, beginning algebra. If you have a linear equation that is just y equals some constant, that's going to be a horizontal line. Let me show you what I mean by this. Let's pick some x values. If x is 0, what's y? Well, the equation is y equals 2. There's no place to put x into it. So no matter what, y is 2. If x is 1, y is 2. If x is 2, y is 2. Because y is 2 no matter what. Well, let's see. X is 0. Y is 2 is there. X is 1. Y is 2 is there. X is 2. Y is 2 is there. What do we get? We get a horizontal line going through y equals 2. And I'm going to go back and write it using the function notation. Okay? Any questions on that? All right. So now we're going to look at some other problems, which again, this material was introduced back in chapter 3. But at that point in Math 85 and graphing, we weren't using function notation. So the new thing is the function notation. But as we go along, I'm going to review some rules to do with graphing. All right. Okay. The directions say, find an equation for a linear function whose graph has the given characteristics. All right. And we're told that the graph has a slope of 5 and a y-intercept of 0, -3. So a slope of 5 and a y-intercept of -3. So that means that m is 5 and b is -3. Going back up here to the whole, I guess I deleted that, the whole y equals mx plus b thing. So the equation would be y equals 5x minus 3, putting 5 in for the slope, m, and -3 in for b. Now you could write 5x plus -3, but that's extra fluff, so 5x minus 3. The only thing left is I need to use function notation, so I'm going to write f of x equals 5x minus 3. So there is an equation for a linear function that has a slope of 5 and a y-intercept of 0, -3. Any questions on that? So that's talking about what is known as slope intercept form. Y equals mx plus b. All right. Next example. Write an equation for a linear function that has a slope of 1/5 and it passes through the point 10, 1. All right, so again, I'm going to start with y equals mx plus b. I know the slope is 1/5, so m is 1/5. Okay, but I wasn't given the y-intercept. In the previous problem, I was given the y-intercept, but now I'm not. But I am given an ordered pair, so this is an x and a y. So what I'm going to do is I'm going to take the 10, which is the x value, and put it right there. And the 1, which is the y value, and put it right there. So that gives me 1 equals 1/5 times 10 plus b. Simplifying, I can now solve for the y-intercept, that is, solve for the letter b. 1 equals 10 over 5 is 2 over 1. 1 equals 2 plus b. Subtract 2 from both sides, and we get -1 equals b. All right, I know the slope and the y-intercept, so y equals mx plus b. 1/5 x minus 1. All that's left is to use function notation. F of x equals 1/5 x minus 1. So let's check our work. Does that have a slope of 1/5? Yes, it does. Does it go through the point 10, 1? Let's see. F of 10 equals 1/5 times 10 minus 1, which is 2 minus 1. Yep, it checks. So there's our answer for that problem. Any questions about this example? All right. Next example. Write an equation for a linear function that passes through the following 2 points, 1, 7 and -2, 1. Well, again, I'm going to use y equals mx plus b. The problem is I don't know m and I don't know b. However, another formula that goes back to chapter 3 is called the slope formula. M stands for the slope, and the formula looks like this. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And those little subs, I mean subscript. So y sub 2 means y with a subscript of a 2, y sub 1, subscript of a 1. What do those refer to? Well, this is 0.1 and this is 0.2. So this is x sub 1, y sub 1, x sub 2, y sub 2. Okay? So the slope is going to be y sub 2 minus y sub 1. So y sub 2, which is that, minus y sub 1, over x sub 2 minus x sub 1. X sub 2 minus x sub 1. Okay? 1 minus 7 is -6. -2 minus 1 more is -3. -6 over -3 is 2. So the slope is 2. Okay? So I used the 2 points to determine that the slope was 2. Any questions about that? Tell you what, let's take those 2 points and let's go back here for a minute. Let's see. Hang on. What was it? 1, 7 and -2, 1. 1, 7 and -2, 1. So this goes up 6 and over 3. And 6 over 3 is 2. So the slope is up 2 over 1, up 2 over 1. Okay, just kind of showing you graphically what's going on there. Okay, so the slope is 2. So that's going to go right there. So y equals 2x plus b. Now, in a previous problem, I needed to find b, and I took an ordered pair and plugged it in for x and y. Here I have 2 ordered pairs. I can pick either one of them, but don't pick an x from 0.1 and a y from 0.2. You've got to use the same point. So let's use 0.1. So 1 is going to go in for x, and 7 is going to go in for y. So 7 equals 2 plus b, subtract 2, b equals 5. So the slope is 2, the y-intercept is 5, y equals mx plus b, y equals 2x plus 5. Using function notation, f of x equals 2x plus 5. Are you okay with this? Lots more to come. All right. We good to go on? Okay. Passes, this is writing an equation for a linear function that passes through the point 3, 0. So passes through 3, 0 and is parallel to, and that's what that means, parallel to the graph of g of x equals -2/3 x minus 4. Okay. Now, parallel lines have the same slope. So we're looking for a line or an equation of a line that passes through that point and it's parallel to this line. This graph, g of x, or this linear function, g of x equals -2/3 x minus 4, okay, has a slope that's -2/3. Y equals mx plus b. So the coefficient of x is the slope. Parallel lines have the same slope. So the slope of the line we're looking for is also going to be negative 2/3 because they're parallel. So they have the same slope. So we took this line here and we said, oh, the slope is negative 2/3. It's going to be the same slope. So now we're going to use y equals mx plus b, but we know that m is negative 2/3. So now we need to find b. Well, we've got an ordered pair that's on the new line. So x is 3 and y is 0. 0 equals negative 2/3. Let me write that a little better. That's negative 2/3 times 3 plus 2. The 3's reduced down. 0 equals negative 2 plus b. Add 2 to both sides, b equals 2. So I know the slope, I know the y-intercept. Y equals mx plus b. F of x equals negative 2/3 x plus 2. All right, so if this is correct, this should have a slope of negative 2/3, same as the original one. Yes, it does. And it should go through the point 3, 0. Well, what's f of 3? It's negative 2/3 times 3 plus 2, which is negative 2 plus 2, which is 0. So it checks. So there's our solution. Okay. Next example. Write an equation for a linear function that passes through 1, 2, so the point 1, 2, and is perpendicular to the graph of, let's see here, g of x equals negative x over 6 plus 1. All right, now, parallel lines have the same slope, okay? Parallel lines. Perpendicular lines, the slopes are opposite reciprocals or negative reciprocals. Before we go on with that problem, let's go through that again. Let's say that line 1 is parallel to line 2. If the slope of line 1 is 2/3, the slope of line 2 would be the same. Parallel lines have the same slope. Let's say that line 3 is perpendicular to line 4. If the slope of line 3 is 4/7, the slope of line 4 would be negative 7/4. Parallel lines have the same slope. Perpendicular lines, the slopes are negative or opposite reciprocals. So you flip it over and you change the sign when they're perpendicular. Okay. Now, all these rules that I've been laying on you are back there in chapter 3 if you want to go back and look at them in, in great detail. But let's go back here. Okay. So first of all, let's take a look at this. Well, if this is y equals mx plus b, let's see, g of x equals negative x over 6. Isn't that like negative 1/6 x? So the slope would be negative 1/6. You see that, the coefficient of x? So what's the slope over here for the line that's perpendicular? That would be positive 6 over 1. We're going to flip it over, negative 1/6. The reciprocal is negative 6 over 1, and change the sign of it, make it the opposite, or the negation thereof. So the slope of the line we're looking for is 6, or 6 over 1. So y equals mx plus b. 6 goes right there. Y equals 6x plus b. I've got an ordered pair. I can plug 1 in for x and 2 in for y. 2 equals 6 plus b. Subtract 6. Negative 4 equals b. So I've got the new slope and the new y-intercept. Don't use the old slope. That was just so we could take its negative reciprocal. So now y equals 6x minus 4, or f of x equals 6x minus 4. I know what you're thinking. You're thinking, stop, my brain is full. We're almost done. I know, a lot of material here. See, this is the bummer about waiting. Like if you just took Math 85, this should all still be up there fresh. If it's been a while, then you got to, clean out the cobwebs and figure out what's going on there. All right. Now, it says, write an equation for a linear function whose graph is horizontal and it passes through the point -8, 12. Well, a while ago, and I think that let's see. Oh, it's still here. We graphed f of x equals 2. And what did we get? A horizontal line, okay? So an equation in the form of y equals a number, y equals a constant, the graph is a horizontal line. So now going down here, we've got a horizontal line, which means it's going to be y equals a constant or a number. Well, what number is y? It's 12. So y equals 12, or f of x equals 12 would be the equation that is of a horizontal line that passes through -8, 12. Let's do it a different way. If I were to graph the point -8, let's see, -8, 12. So we'll call this -8, and this is 12. Okay, a horizontal line passing to that point would be y equals 12, because all the y values would be 12, and as a function, it's written like that. Okay. So let's do a review of all these rules that I've been laying on you, okay? Let's see, we had y equals mx plus b. That's the slope intercept form, where m is the slope and b is the y-intercept. We've had the slope formula, m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's where we take the x and y values from 2 points and plug them in there to get the slope. We've said that y equals a constant is the, let's see, y equals constant is a graph of a horizontal line. Let's see, what else have we done? Oh, parallel lines have the same slope. Perpendicular lines have negative reciprocal slopes. And let's see, what else? Y equals mx, that passes through parallels. Yeah, I think those are the ones that we've looked at today. Okay. All right, now this leads us to an application problem. Here is the problem. It says, nurses. The demand for full-time registered nurses in the United States can be modeled by a linear function. So we're talking y equals mx plus b, or f of x equals mx plus b, linear function. In 2005, approximately and don't panic about all these numbers, I'm going to write them down here eventually. I'm just going to read through the whole thing first. In 2005, approximately 2,175,500 nurses were needed. By the year 2015, that number is expected to increase to about 2,586,500. Now, obviously, this problem is about 10 years old. Be curious to know if that was really true. But anyway, all right. It says, let T be the number of years after 2000. So T equals number of years. Before this was a hashtag, it also stood for number of years after 2000. And N is the number of full-time registered nurses. Okay, we'll just say nurses. Okay, so T is the number of years after 2000, N is the number of years nurses. It says, write a linear function N of T to model the demand for nurses. Okay, so N of T. Now, what that tells us is that T is the input and N is the output. So our ordered pairs are going to be in the form T comma N. Okay? And trying to write a function y equals mx plus b, it's actually going to be N of T equals mt plus b, because our input is going to be T and our output is going to be N. Okay? So we're going to be talking mx plus b, but it's T is the input and N is the output eventually. All right. So because of this, I know time is the input, the number of years nurses is the output. Okay. Now let's go back and read the problem again. It says, the demand for full-time registered nurses in the United States can be modeled by a linear function. In 2005, so that's a time, approximately 2,175,500 nurses were needed. That's a number of nurses. Okay, so T is the number of years after 2000. So in 2005, T would be 5. So we're not going to write 2005, we're just going to write 5 because it's 5 years after 2000. Okay, it's kind of a time shift thing. The number of nurses, 2,175,500. So our first ordered pair is that in 2005, 5 years after 2000, there were 2,175,500 nurses. That's our first ordered pair. Okay. It goes on to say, by the year 2015, that's 15 years after the year 2000, that number is expected to increase to about 2,586,500. So what I've done is I've extracted 2 ordered pairs of information from the problem. In the year 2005, there were a certain number of nurses. In the year 2015, there were a certain number of nurses, okay? But we're not using 2005 and 2015 because we're using T as the number of years after 2000, okay? So here's our 2 points. We'll call this point 1 and this point 2. If you'll recall, earlier we did a problem where given 2 ordered pairs, let's see if we can find that one. Given 2 ordered pairs, find the equation of the function that passes through these 2 ordered pairs. What did we do? We found the slope, plugged that in, took one of the points to find the y-intercept, and bada boom, bada bing, got our equation. So here we go, okay? The slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Y sub 2 is going to be 2,586,500. Y sub 1 is 2,175,500. X sub 2 is 15. X sub 1 is 5. All right, it's calculator time. Let's see here. 2,586,500 minus 2,586,500. Okay, I see what I did wrong. I looked at the wrong place. Let's try that again. 2,586,500 minus this number, not that one, minus 2,175,500 is 411,000. 15 minus 5 is 10. Well, 411,000 divided by 10, we could cross out a 0 and cross out a 0, and the slope is 41100. So our slope is 41,100. Okay? Any questions before I go on to finish this? So now I'm going to plug that in there. So y equals 41,100 x plus b. And again, I'm using x and y, though ultimately it's going to be n and t. Take one of these, let's take this ordered pair. 5 goes in there and 2,175,500 goes in there. So I've got 2,175,500 equals 41,100 times 5 plus b. 2,175,500 equals, let's see here, 41,100 times 5 is 205,500 plus b. We're going to subtract 205,500 from both sides. So let's see, on the left, 2,175,500 minus 205,500, and I get 197,000 equals b. So my slope is 41,100. My y-intercept is 1,970,000. So I'm going to take those two pieces of information. Was it 197,000? Okay. So I took my slope and my y-intercept. So y equals 41,100 x plus 1,970,000. But actually, we were supposed to use t as our input and n as our output. So n of t equals 41,100 t plus 1,970,000. Okay. So there's our function using t and n. I went ahead and used the formulas using x and y because that's what we're used to, and then switched it to the correct variables at the end. All right, now there's a follow-up question. It says, use your answer to part A to predict the number of full-time registered nurses that will be needed in the year 2025 if the trend continues. So in the year 2025. Okay, here comes the Jeopardy bonus question. Let's see if anybody can answer this question. All right. Using function language, can you tell me what they want us to find? It's going to be a very short, concise statement. They want us to find, and then can you tell me what they want us to find using function language? Anybody? Okay. They want us to find n of 25. Now, where did I get that? Remember, this is how many years past the year 2000? 25. So I'm going to put 25 in for t. So I'm going to find n of 25. Does that make sense? And how do I find that? Well, I put 25 in for t, and then I do the calculations. Let's see, 41,100 times 25 plus 1,970,000, and I'm getting 2,997,500 nurses. So based on the linear function that we created by extracting two ordered pairs from the story, if this trend continues, the prediction would be that in the year 2025, there would be what, almost 3 million nurses needed. Now, we're close to that now, but anyway, all right. Any questions about this? All righty. So I know you've got a lot on your plates for tonight. Section 8.2, there's part 1 and part 2. I will be back tomorrow morning at 10 o'clock with an office hour. And then we'll continue on in chapter 8 tomorrow. Anyway, I'm going to go ahead and stop the recording.